really looking forward to talking today about this idea of, will you be looking to choose AI to help optimize industrial performance? So what better way to get started than just sort of talking about what we mean by the term industrial AI and why you would want to consider it at all. So industrial AI is a little bit of a vague and an overarching term. What we're talking about today is really the application of AI in industrial settings, and more specifically the use of machine learning. So the use of modeling techniques which can be a little bit more flexible and adaptable than some other traditional modeling techniques, where we're actually able to essentially build models that learn from the data we collect from specific assets, so that we can build models that are well tuned to actual operating environments, and thinking through with that flexibility and that power how we actually do that well, and bring physics and engineering along and be our sort of guiding North Star to how we want to do that as well. So just to hone in really on that idea of machine learning being really the focus within industrial AI, just I guess a bit of a overview of how machine learning fits in. Again, you'll probably be able to see a few different definitions or ideas around what industrial AI includes, but what we're sort of focused on is really this lighter blue circle of where machine learning fits in to industrial settings. And there's a lot of terminology here. Some of these things are kind of related to each other, or kind of synonyms in some ways, but what I guess we want to really simplify the message here is that for an engineer who's not necessarily looking to design machine learning themselves, they just want to be able to apply it to optimize whatever systems they're dealing with. That's what we really want to hone in on, is this actual statement here, which is it's simply, if we forget everything else, all the different terminology, we're really just trying to help engineers with detection, prediction, and optimization. So in industrial settings where we've got a lot of data, a lot of information to deal with, how do we actually bring machine learning in to help us better detect things, predict things, and optimize things? And it's as simple as that when we actually look at how it makes sense in an industrial setting. And so just to, I guess, maybe expand on that idea of why detection, prediction, and optimization are kind of key capabilities within engineering, we can also just even come up a layer and say, why do we want to do even any of that? And I think a key sort of concept is to think about the ways that an engineer in an operational setting is looking to use data to make decisions. Really, that's what we're trying to do. We're trying to make decisions based on data, and trying to do that as efficiently and as effectively as we can. And we often talk about making data-driven decisions, but often we don't necessarily map out the journey. You know, there's a one arrow here and a bit of a gap, but there's actually a lot that goes on between data coming from a sensor and making decisions. And this is where models come in. Just high-level models, whether it's machine learning or not, help us simplify or represent a real-world system. So the whole idea is a model makes our life easier. It means that we're not having to look at thousands or millions of rows of data points and somehow process that with our own abilities on our own. We try and use models to feed that data through, and pretty much go from a lot of data into a simpler form that we can actually kind of use and make decisions from. But you can't just throw data into a model. You've got to actually process that in some way. And it's also worth calling that out, that there's some pre-processing here. There are steps involved to make sure that the data is in the right form. It could be because models are in a certain software, or they require certain data sets in a certain form. But basically, there's a step involved in turning data into a form and processing it into a form that makes sense for models. And we also don't really go from models straight to decisions. We have to go through that step of actually looking at what it's telling us, and going through the process of analyzing it, analyzing the outputs of models, and deriving an insight from it, trying to figure out, we've done some piece of analysis as an engineer and thought, right, what is this telling me? And you have an aha moment and go, right, I know what I need to do now. And that's then what leads you to make some sort of decision. But models aren't, whilst they endeavor to make our life easier, they also need to then be maintained. You have to actually maintain and optimize a model, which is quite interesting, because often we think about optimizing a system and not actually thinking about the fact that when we're using different tools, you've actually got to optimize a model and hope that that model represents your reality well. So you're not wasting your time optimizing something that doesn't even work. So you've got to keep configuring, maintaining these models. In the case of machine learning, you've got to retrain models. That's a bit of a additional task or something that needs to happen so that these models are up to date and working well. But basically what we're saying is models don't come without some, let's say, time invested to keep them maintained. And just because you've made a decision doesn't mean that something's happened. You might have done some really detailed analysis and thought, I know what to do, but then you've actually got to act on it. You've got to either change a set point in a control system or send a work request to another team, whatever it might be. There is actually a step involved in actually taking action based on a decision that you've made. And once you've made a decision and you've taken an action, that's then a feedback loop that we look at as engineers and go, right, okay, what did we learn? And we go through after action reviews or post event lessons learned sessions to say, what went well, what didn't go well, and how do we then learn from that and restart this cycle of, right, we've got this data now from our system and we've got data from what we've tried. How do we then become really effective at learning from that and building a bit of a feedback loop so we get better and better as we operate? These are complex systems, and we're teams are always changing and we're always evolving as an organization. So how do we make sure we have a good feedback loop? So the question is what in this process should be manual, what should be automated, and what should be potentially autonomous? Now, I'll admit that even maybe a couple of years ago, I didn't really care for the difference between the word automated and autonomous, but it is quite important, even though they start with the same 4 letters. Automated and autonomous do mean different things, particularly in this context of understanding what's the role of machine learning in the way that we work. But something that's manual, you're doing yourself. There is essentially a lot of time and effort involved. Automated could be some sort of rules-based system or something that you've programmed specific steps to take. It's basically a recipe. There's no room for creativity or, let's say, innovation or change. It is really about follow these steps, and there is a role for automation when we need something explicit and defined. Autonomy or autonomous capabilities are where we actually want something to, we know what we want, but because of the dynamic or complex nature of a system, we don't actually know exactly what, the 10 steps are that we need to map out, but we know that we have objectives that we want this system to achieve. And that's where machine learning can come in, and we'll talk more about how to actually sort of turn that into a couple of criteria to identify where autonomy makes sense. But essentially what we're trying to get at here is if you look at all these boxes and you were to say what should be manual, what should be automated, and what should be autonomous, that's when you might start to think about where machine learning makes sense in this overall process. For example, you might say if we want to collect data, we don't want to collect data manually. We want that to be an automated piece of technology that can process data, collect data, and go into a pre-processing step. Again, we know what data we want to process, we know what we want to aggregate. These 2 steps could be, or we'd ideally like them to be automated. And then you might look at where autonomous models make sense in some of the decisions that we're making. And it's a little bit kind of hard to understand in context, which is why we'll go into use cases shortly. But I just wanted to paint this picture of, as an engineer, you've only got a finite amount of time. So you've got to think about what technologies and tools you use to get from data all the way through to action, and how do you learn really efficiently. So why industrial AI? A bit of a long journey to get to why industrial AI, but it's all about trying to make equipment more intelligent so that it's less, if it's more intelligent, then that's what's going to be able to drive more autonomous operations, because we're not going to have to, hold equipment's hand as tightly. It will be able to adjust and adapt in the dynamic environment that it's operating in. And that's what's going to help your performance overall become more optimized, because it actually entirely changes and simplifies the engineering processes we follow when the equipment itself doesn't demand more manual and repetitive tasks. So the whole concept of industrial AI is how do we actually make machines smarter so that operations become simpler?